Welcome to the Sleepy Mechanic. Tonight we're going to spend some quiet and relaxed time together in the garage while we slowly explore how a car engine works. There's no need to focus too hard, and there's nothing you need to remember perfectly. This is simply a calm mechanical story designed to help you relax while learning a little about one of the most interesting machines ever created. So wherever you are right now, perhaps lying comfortably in bed or resting after a long day, allow your body to relax and let your breathing slow down just a little. Imagine for a moment that you are sitting in a quiet garage late at night. The lights are soft, the tools are resting on the workbench, and somewhere nearby a car engine has just finished running and is ticking gently as the metal cools. Mechanics often enjoy moments like this, when the shop is quiet and there is time to think slowly about how machines work. Tonight, we are going to do the same thing together. We'll slowly explore the ideas behind engines, the parts inside them, and the calm repeating rhythm that allows a car to move down the road. You don't need to stay fully focused on every detail. If your mind begins to wander or your eyes start to feel heavy, that is completely fine. You can simply listen to the slow explanation, almost like the steady sound of an engine idling quietly in the background. So get comfortable, take a slow breath, and let's begin our gentle journey into the world of car engines. The early idea of engines. Long before cars existed, people were already searching for ways to turn energy into movement. Humans have always needed machines to help move things, whether it was lifting heavy loads, turning wheels, or traveling long distances. Early engineers discovered that heat could be used to create motion. One of the first major inventions based on this idea was the steam engine. Steam engines worked by heating water until it turned into steam. As the steam expanded, it created pressure, and that pressure could push against mechanical parts and make them move. These early engines powered factories, trains, and ships, but they were very large and heavy machines. They required big boilers, large amounts of water, and constant maintenance. Over time, inventors began wondering if there might be a smaller and more efficient way to create power. Instead of producing steam outside the engine, they started experimenting with burning fuel directly inside a small chamber. This idea slowly developed into what we now call the internal combustion engine. The words internal combustion simply mean that fuel burns inside the engine itself. When fuel burns, it releases energy, and that energy can push against moving parts inside the machine. During the 1800s, engineers continued experimenting with different engine designs. One of the most important ideas that appeared during this time was the four-stroke cycle. This cycle describes the repeating process that most gasoline engines use to create power. The engine first pulls in air and fuel, then compresses the mixture, then ignites it so it burns and produces power, and finally pushes the exhaust gases out of the cylinder. This simple cycle repeats again and again while the engine runs. Even today, most gasoline engines still follow this same basic rhythm: intake, compression, power, and exhaust. Mechanics sometimes describe it almost like breathing. The engine breathes in air and fuel, compresses the mixture, releases energy, and then breathes out again. This repeating motion allows engines to run smoothly for long periods of time. As engines improved, they became smaller, lighter, and more reliable. Eventually, they became compact enough to power early automobiles. These early vehicles were simple compared to modern cars, but they proved that a small engine could move a person down the road. From that point forward, engineers continued improving the design. Materials became stronger, fuel systems became more precise, and engines became capable of running for thousands of hours. Today, the basic idea is still the same. Fuel burns inside the engine, and the energy from that combustion is turned into motion. But inside that simple idea, there is a surprisingly elegant mechanical system made of many parts working together. In order to understand how all of those parts cooperate, we first need to explore the basic process that creates the energy itself. That process is combustion. The calm process of combustion. Combustion is the heart of every gasoline engine. The word combustion simply means burning fuel. But inside an engine, the burning process is carefully controlled and happens in a repeating rhythm. To understand it, we can imagine a very simple situation. Think about lighting a small candle in a quiet room. The candle burns slowly as the wax and oxygen combine to create heat and light. Inside an engine, something similar happens. But instead of burning wax slowly, the engine burns a mixture of fuel and air very quickly inside a sealed metal chamber. The fuel used in most car engines is gasoline. Gasoline contains a large amount of stored chemical energy. When it mixes with oxygen and ignites, it releases that energy as heat and expanding gases. Those expanding gases are extremely important because they create pressure, and pressure is what allows the engine to produce mechanical motion. Inside each cylinder of the engine, there is a small space where fuel and air can mix together. First, the engine pulls fresh air into the cylinder. This air contains oxygen, which is necessary for combustion. Then the fuel system adds a small amount of gasoline to the incoming air, creating a mixture that can burn. Once the mixture is inside the cylinder, the piston begins to move upward. As the piston rises, it compresses the air and fuel mixture into a smaller and smaller space. Compression increases the pressure and temperature of the mixture, preparing it to release energy efficiently when it ignites. At the right moment, a spark plug produces a small electrical spark. Even though the spark is tiny, it is enough to ignite the compressed mixture. When the mixture ignites, the fuel burns rapidly and the gases expand. This expansion pushes the piston downward with force. That downward motion is the moment when the engine produces power. The piston then moves upward again to push the remaining exhaust gases out of the cylinder. Once the cylinder is clear, the cycle begins again with fresh air and fuel entering the chamber. This entire process happens extremely quickly. In many engines, each cylinder completes this cycle dozens of times every second. Yet even though the process is fast, it remains very controlled. Each spark occurs at a precise moment, and each piston follows the same repeating pattern. Because of this rhythm, the engine can run smoothly for long periods of time. From the outside, it may simply sound like a quiet hum, but inside the engine, thousands of tiny combustion events are happening every minute. Each one produces a small push, and when those pushes happen again and again, they combine to create the steady rotating force that eventually turns the wheels of the car. But in order for this combustion process to work safely, the engine needs a strong structure to contain the heat and pressure. That structure is the engine block, the heavy metal foundation that holds the cylinders and supports the moving parts. In the next chapter, we will slowly explore how the engine block forms the core of the entire engine. The engine block. The engine block is the foundation of the entire engine and one of the most important structural components in any car. When mechanics talk about an engine, they often imagine the engine block first because almost every other part attaches to it in some way. The block is usually made from strong metal such as cast iron or aluminum, materials chosen because they can handle high temperatures and strong mechanical forces for long periods of time. Inside the engine block are the cylinders, which are smooth round chambers where the pistons move up and down while the engine runs. Each cylinder must be manufactured with extremely high precision. The walls of the cylinder need to be smooth enough for the piston to move easily, but also tight enough to keep the combustion gases sealed inside the chamber. If these gases were able to escape too easily, the engine would lose power and efficiency. This is why the machining process for an engine block is very precise and carefully controlled. The engine block also contains several internal passages that are hidden from view when the engine is assembled. Some of these passages are designed to carry coolant through the block. Coolant is a liquid mixture that absorbs heat from the engine while it operates. Because combustion creates very high temperatures inside the cylinders, the engine must constantly move heat away from its internal components. The coolant flows through these passages, absorbs heat from the metal, and then travels to the radiator where the heat can be released into the surrounding air. In addition to coolant passages, the engine block also contains small oil channels. These passages allow engine oil to flow through the block and reach important moving components such as bearings and crankshaft journals. The oil forms a thin protective film between metal surfaces, so they can move smoothly without grinding against each other. Without this lubrication, the internal parts of the engine would quickly wear out. Another critical job of the engine block is to support the crankshaft. The crankshaft sits in the lower portion of the block and is held in place by large bearings. These bearings allow the crankshaft to rotate smoothly while still supporting the powerful forces created during combustion. When the pistons push down during the power stroke, they transfer force through connecting rods to the crankshaft. The engine block must be strong enough to absorb these forces while keeping all of the moving components aligned. When you look at an engine block by itself, it may appear to be a simple piece of metal, but in reality it is a carefully engineered structure that supports the entire mechanical system. Every hole, surface, and passage has a specific purpose. The cylinders guide the pistons, the oil passages protect moving parts, and the coolant channels manage heat. While the pistons move rapidly and the crankshaft spins continuously, the engine block remains steady, quietly holding everything together and allowing the engine to operate smoothly for thousands of miles. Pistons. Inside each cylinder of the engine, there is a component called a piston. The piston is one of the most important moving parts inside the engine, because it is directly involved in turning the energy from combustion into mechanical motion. If you imagine the cylinder as a hollow metal tube, the piston sits inside that tube and moves up and down while the engine runs. This motion may seem simple at first, but it is part of a carefully timed mechanical rhythm that repeats thousands of times every minute. When the engine begins the intake part of its cycle, the piston moves downward inside the cylinder. As it moves down, it creates space inside the chamber, and this allows the engine to pull in fresh air and fuel. Once the cylinder is filled with the air and fuel mixture, the piston begins moving upward again. As it rises, it compresses the mixture into a smaller and smaller space. This process is known as compression. Compression is important because it allows the fuel and air mixture to release its energy more efficiently when it ignites. When the piston reaches the top of the cylinder, the spark plug produces a small spark. This spark ignites the compressed fuel and air mixture, and combustion begins. The burning fuel creates rapidly expanding gases, and those gases push down on the piston with force. This downward push is known as the power stroke, and it is the moment when the engine produces useful mechanical energy. The piston then begins moving upward again to push the remaining exhaust gases out of the cylinder so that the cycle can begin again. This entire process happens extremely quickly. In many engines, a piston may move up and down dozens of times every second. Even though this movement is very fast, it remains smooth and controlled because the piston is carefully designed to handle heat, pressure, and constant motion. Pistons are usually made from aluminum alloy because aluminum is lightweight and can conduct heat well. A lighter piston allows the engine to run more smoothly and reduces the stress placed on other components. Around the outer edge of the piston are small grooves that hold piston rings. These rings serve several important purposes. First, they help seal the combustion chamber so that the expanding gases cannot escape past the piston. This keeps the engine efficient and allows more energy from combustion to be used for power. Second, the rings help control the thin layer of oil that coats the cylinder walls. This oil reduces friction between the piston and the cylinder so that the piston can slide smoothly while the engine operates. Without this lubrication, the metal surfaces would quickly wear out. Pistons must also be able to handle extremely high temperatures because combustion creates a great deal of heat inside the cylinder. During operation, the piston repeatedly absorbs heat from the burning fuel and then transfers some of that heat to the cylinder walls and engine cooling system. Engineers design pistons carefully so that they can expand slightly as they heat up while still maintaining a proper fit inside the cylinder. When you imagine the pistons inside an engine, you can picture them moving up and down in a steady mechanical rhythm. Each piston performs the same motion again and again while the engine runs. Their movement may seem simple, but together they create the force that drives the entire machine. However, the up and down motion of the pistons alone cannot turn the wheels of a car. That motion must be converted into rotation. This is where another important component comes into the picture, the crankshaft. The crankshaft. While pistons move up and down inside the cylinders, the wheels of a car need rotational motion in order to turn. The crankshaft is the component that converts the piston's vertical movement into the rotating motion that eventually drives the vehicle forward. The crankshaft sits in the lower part of the engine block and is connected to each piston by a connecting rod. As a piston moves downward during the power stroke, it pushes on the connecting rod, and the connecting rod transfers that force to the crankshaft. Because of the way the crankshaft is shaped, this push causes it to rotate. Once the crankshaft begins rotating, it continues spinning smoothly as the other pistons complete their cycles and push on it in sequence. The crankshaft is a long metal shaft with carefully shaped sections called journals and crank throws. These shapes allow the connecting rods to attach to the shaft at slightly offset positions. This offset design is what allows the up and down motion of the pistons to produce rotation. When the pistons move, they apply force to these offset sections, causing the crankshaft to spin. Even though the crankshaft may appear simple at first glance, it is actually a very carefully engineered component. It must be extremely strong because it experiences the combined forces of all the pistons during combustion. At the same time, it must also be precisely balanced so that the engine can run smoothly without excessive vibration. Engineers spend a great deal of time designing crankshafts so that they maintain this balance even while rotating thousands of times per minute. As the crankshaft spins, it transfers its rotational motion to the rest of the vehicle's drivetrain. The rotation travels through the flywheel and into the transmission. From there, the motion eventually reaches the drive shaft and the wheels. This chain of mechanical movement begins with the small combustion events inside the cylinders and ends with the car moving down the road. Even though drivers rarely see the crankshaft while using their vehicles, it plays a central role in transforming the energy of burning fuel into usable motion. Hidden deep inside the engine block, the crankshaft rotates steadily while the pistons continue their repeating cycles above it. The careful coordination between pistons and crankshaft creates the smooth mechanical rhythm that allows an engine to run quietly for long periods of time. Yet, for the engine to continue operating efficiently, it must also control when air and fuel enter the cylinders and when exhaust gases leave. This control is handled by another set of components known as valves and the camshaft, which we will explore in the next chapter. Valves and camshafts. For an engine to operate smoothly, it must carefully control the flow of air, fuel, and exhaust gases. This control is handled by components known as valves. Valves act like small mechanical doors that open and close passages leading into and out of each cylinder. When the intake valve opens, fresh air and fuel can enter the cylinder. When the exhaust valve opens, the burned gases can leave after combustion has taken place. Even though the idea seems simple, the timing of these valves is extremely important. They must open and close at very precise moments while the engine runs. If they opened too early or too late, the engine would not operate efficiently and combustion would not occur properly. The component responsible for controlling the movement of the valves is called the camshaft. The camshaft is a rotating shaft with specially shaped lobes along its length. As the camshaft turns, these lobes push against the valves, causing them to open. When the lobe rotates away, the valve closes again with the help of a spring. This motion repeats again and again while the engine runs. The camshaft rotates in synchronization with the crankshaft so that the valves open at exactly the right moment during each cycle of the piston. For example, when the piston moves downward during the intake stroke, the intake valve opens to allow air and fuel to enter the cylinder. Later, when the piston moves upward during the exhaust stroke, the exhaust valve opens so the burned gases can leave the chamber. This precise coordination allows the engine to breathe properly. Many engines have multiple valves for each cylinder. Some engines use 2 valves per cylinder, while others use 4 or even more. Having more valves allows air and fuel to flow more easily into the cylinder and allows exhaust gases to leave more efficiently. This can improve engine performance and efficiency. The camshaft itself is driven by the crankshaft through a timing belt or timing chain. This connection ensures that both shafts rotate in perfect synchronization. Because the pistons and valves move in the same space inside the cylinder at different times, correct timing is essential. If the timing were incorrect, the valves could open at the wrong moment and collide with the pistons. That is why timing systems are carefully designed and maintained. When everything works together correctly, the valves open and close in a quiet, repeating rhythm that allows the engine to inhale fresh air and exhale exhaust gases continuously. This breathing process supports the combustion cycle that powers the entire machine. However, for combustion to continue, the engine must also receive a steady supply of fuel. This task is handled by the fuel system. The fuel system. The fuel system is responsible for delivering gasoline from the fuel tank to the engine in the correct amount and at the correct time. Although it may seem simple to just send fuel toward the engine, the process actually requires careful control. Modern engines rely on a precise mixture of air and fuel to operate efficiently. Too much fuel can cause poor efficiency and increased emissions, while too little fuel can cause the engine to run poorly or lose power. The process begins at the fuel tank, where gasoline is stored. Inside the tank, a fuel pump pushes fuel through fuel lines toward the engine. This pump ensures that fuel travels at the proper pressure so it can reach the engine consistently. Once the fuel arrives at the engine, it reaches the fuel injectors. Fuel injectors are small components that spray gasoline into the air, entering the intake system. Instead of simply pouring fuel into the engine, the injectors create a fine mist of tiny droplets. This mist mixes with incoming air to create a fuel and air mixture that can burn efficiently. The injectors are controlled by the vehicle's engine computer. Sensors throughout the engine measure factors such as airflow, engine temperature, and throttle position. Using this information, the computer calculates exactly how much fuel should be injected into each cylinder. The injectors then open for a very brief moment to deliver that precise amount of fuel. This process repeats continuously while the engine runs. The careful control of fuel delivery allows modern engines to operate efficiently and smoothly under many different conditions. Whether the car is idling quietly or accelerating on the highway, the fuel system constantly adjusts the amount of fuel entering the engine. Even though drivers rarely see the fuel system in action, it quietly works in the background to maintain the proper mixture for combustion. Once the air and fuel mixture enters the cylinder, it must be ignited so that combustion can begin. This is the responsibility of another important system within the engine, the ignition system. The ignition system. After the air and fuel mixture enters the cylinder and becomes compressed by the rising piston, it must be ignited so that combustion can occur. This is the task of the ignition system. The ignition system creates the spark that starts the burning process inside the cylinder. The most recognizable part of this system is the spark plug. Each cylinder contains a spark plug positioned near the top of the combustion chamber. When the time is right, the spark plug produces a small but powerful electrical spark. Even though the spark is tiny, it carries enough energy to ignite the compressed mixture of air and fuel. When the spark occurs, the mixture begins to burn rapidly, and the expanding gases push the piston downward during the power stroke. For the engine to operate smoothly, the spark must occur at exactly the correct moment. If the spark happens too early, the mixture may begin burning before the piston reaches the top of the cylinder. If it happens too late, the expanding gases may not produce as much useful force. Because of this, the ignition timing must be carefully controlled. Modern vehicles use electronic control systems to manage ignition timing with great precision. Sensors monitor engine speed, load, and temperature. The engine computer then determines the exact moment when each spark plug should fire. This precise timing ensures that combustion occurs efficiently and smoothly during every cycle. Earlier engines relied on mechanical distributors to control ignition timing. While those systems worked well for many years, modern electronic ignition systems are more accurate and require less maintenance. Regardless of the technology used, the purpose of the ignition system remains the same. It provides the spark that starts combustion and allows the engine to convert fuel and air into mechanical power. As the engine continues running and combustion events repeat inside the cylinders, a large amount of heat is produced. Managing this heat is essential for keeping the engine operating safely and efficiently. That is why engines rely on another important system designed to control temperature, known as the cooling system. The cooling system. While the engine runs, it produces a significant amount of heat. Each time fuel burns inside the cylinders, energy is released, and a large portion of that energy becomes heat. If this heat were allowed to build up without control, the engine could quickly become damaged. Metal components could expand too much, oil could lose its ability to lubricate properly, and important parts could begin to wear out. To prevent this, the engine uses a cooling system designed to manage temperature and keep everything operating within a safe range. The cooling system works by circulating a liquid called coolant through passages inside the engine. These passages run through the engine block and cylinder head, allowing the coolant to flow around the hot metal surfaces that surround the combustion chambers. As the coolant moves through the engine, it absorbs heat from these components. Once the coolant has absorbed heat, it travels through hoses toward the radiator located at the front of the vehicle. The radiator is designed with many thin metal fins and tubes that allow air to pass through easily. As the car moves forward, air flows through the radiator and carries heat away from the coolant. Even when the vehicle is not moving, a cooling fan helps pull air through the radiator to remove heat. After releasing heat in the radiator, the coolant flows back toward the engine to repeat the process again. This continuous circulation allows the engine to maintain a stable operating temperature even while combustion events continue inside the cylinders. The cooling system also includes a thermostat, which helps regulate temperature by controlling how much coolant flows through the radiator. When the engine is cold, the thermostat remains closed so the engine can warm up quickly. Once the proper temperature is reached, the thermostat opens and allows coolant to circulate more freely. This careful control of temperature helps the engine operate efficiently and prevents overheating. The lubrication system. Inside an engine, many metal parts move against each other at high speeds. Pistons slide within cylinders, crankshafts rotate in bearings, and camshafts turn while opening and closing valves. Without proper lubrication, these moving surfaces would quickly generate friction and wear. The lubrication system prevents this by circulating engine oil throughout the engine. Oil begins its journey in the oil pan located at the bottom of the engine. From there, an oil pump draws the oil upward and pushes it through small passages known as oil galleries. These passages guide the oil toward important components such as crankshaft bearings, connecting rods, and camshaft journals. As the oil flows across these surfaces, it forms a thin protective layer between the metal parts. This thin film reduces friction and allows the components to move smoothly even under heavy loads. Oil also helps carry heat away from internal parts and transports tiny particles created by normal engine wear. Before the oil continues circulating, it passes through an oil filter. The filter removes dirt and small debris so that clean oil continues protecting the engine. This cycle repeats constantly while the engine runs. Even though the lubrication system operates quietly in the background, it plays a critical role in extending the life of the engine and ensuring smooth operation. Common engine problems. Even though engines are carefully engineered machines, they can still develop problems over time. Many of these issues appear gradually as parts wear out after many hours of operation. One common problem is overheating. If the cooling system fails or coolant levels become too low, the engine may begin to run hotter than normal. Another issue can be oil leaks. Seals and gaskets are used throughout the engine to keep oil inside, but as these materials age, they may begin to wear or crack, allowing small amounts of oil to escape. Engines may also experience loss of compression. Compression is important because it allows the air and fuel mixture to ignite efficiently. If piston rings wear out or valves fail to seal properly, some of the pressure inside the cylinder may escape. When this happens, the engine may lose power or run less smoothly. Fuel system problems can also occur. Fuel injectors may become clogged or sensors may provide incorrect information to the engine computer. When this happens, the mixture of air and fuel may not be balanced correctly. Mechanics often listen carefully to engine sounds and observe how the engine behaves to identify these problems. Unusual noises, vibrations, or warning lights can provide clues that something inside the engine is not working as it should. How mechanics diagnose engines. When a mechanic begins diagnosing an engine problem, they usually start with simple observations. They may listen to the engine while it runs, noticing whether the sound is smooth or uneven. They may check fluid levels such as oil and coolant to ensure the engine is receiving proper lubrication and cooling. Modern vehicles also include diagnostic systems that monitor engine performance. Mechanics can connect specialized tools to the vehicle to read diagnostic codes stored by the engine computer. These codes provide information about sensors, ignition timing, fuel delivery, and other systems. From there, the mechanic can perform additional tests to narrow down the cause of the issue. Sometimes the problem may be something simple, like a worn spark plug or a loose hose. Other times it may require more detailed inspection of internal components. Good diagnosis requires patience and careful thinking. Mechanics rely on their understanding of how engines normally operate in order to recognize when something is not quite right. By tracing the problem step by step, they can eventually locate the source and repair the engine. so it runs smoothly again. The exhaust system. Once combustion has taken place inside the cylinder and the piston has completed its power stroke, the burned gases need to leave the engine. This is the job of the exhaust system. The exhaust system quietly guides these gases out of the engine and eventually releases them safely into the air. Each cylinder has an exhaust valve that opens at the correct moment during the exhaust stroke, allowing the piston to push the burned gases out of the chamber. The gases then travel through exhaust manifolds, which are carefully shaped metal channels designed to collect gases from multiple cylinders and direct them into a single path. From the manifolds, the gases pass into the catalytic converter, a special chamber filled with materials that help reduce harmful emissions. The catalytic converter transforms pollutants in the exhaust gases into less harmful compounds, making the engine cleaner and safer for the environment. After the catalytic converter, the gases continue through the muffler. The muffler is designed to reduce the sound produced by the rapid movement of exhaust gases. Inside the muffler, a series of chambers and baffles gently redirect the flow of gases, dissipating energy and lowering noise levels. Finally, the gases exit the vehicle through the tailpipe, completing the journey that began inside the cylinder. While the exhaust system may seem like a simple tube, it is actually a carefully engineered part of the engine. It allows the combustion process to continue efficiently by removing gases quickly and quietly, helps the vehicle meet emissions standards, and keeps the noise of the engine at a calm and controlled level. Mechanics know that a properly functioning exhaust system contributes not only to performance but also to the long-term health of the engine. Clogged or damaged components in the exhaust can cause the engine to run poorly or even overheat. By understanding the quiet rhythm of the exhaust system, one can appreciate how each part of the engine, even the parts that release gases, contributes to the overall calm and efficient operation of the machine. Engine maintenance tips. Even the most carefully engineered engines require attention and care to continue running smoothly. Maintenance is the quiet practice of ensuring that each system inside the engine receives the attention it needs. One of the simplest and most important maintenance tasks is regularly checking and changing the engine oil. Oil lubricates moving parts, reduces friction, carries away heat, and traps small particles of debris. Over time, oil becomes dirty and loses its effectiveness, so changing it at recommended intervals helps the engine continue to run smoothly. Another important practice is monitoring coolant levels and ensuring that the cooling system remains free of leaks. Coolant removes heat from the engine and keeps it operating at a safe temperature. Overheating can cause serious damage, so a mechanic or car owner should check coolant levels and inspect hoses for cracks or leaks. Air filters also play a critical role in engine health. They prevent dust, dirt, and other debris from entering the combustion chamber. A clogged air filter can reduce efficiency and even affect fuel economy. Replacing air filters periodically ensures that the engine continues to breathe properly. Spark plugs and ignition components are also part of routine maintenance. Worn spark plugs can cause misfires, reduce power, and increase fuel consumption. Replacing spark plugs at the recommended intervals helps maintain smooth combustion. The fuel system benefits from occasional cleaning, particularly in engines with direct fuel injection. This helps prevent deposits from forming on injectors and ensures that fuel delivery remains precise. Finally, belts and timing chains should be inspected for wear. These components keep the camshaft and crankshaft synchronized. If they fail, the engine may stop running properly, or worse, components inside the engine could collide. Maintenance may seem like a quiet and repetitive task, but it is the key to long-term engine health. By attending calmly and consistently to oil, coolant, air filters, spark plugs, and belts, a mechanic ensures that the engine continues its steady, rhythmic cycle of intake, compression, power, and exhaust. Regular maintenance allows the engine to remain efficient, smooth, and quiet for many years, and gives drivers the confidence that their vehicle will operate safely whenever they need it. And now our slow journey through the engine is coming to a gentle end. We began with the simple idea of combustion and explored the many parts that work together inside the engine block. Pistons moved up and down. The crankshaft turned that motion into rotation. Valves and camshafts allowed the engine to breathe, and systems for fuel, ignition, cooling, and lubrication quietly supported the entire process. Even though an engine may seem complex at first, it is really a collection of parts working together in a calm, repeating rhythm. Intake, compression, power, and exhaust, repeating again and again while the car moves down the road. If you are still listening, thank you for spending this quiet time in the garage with me. And if you are already drifting towards sleep, then the steady rhythm of the engine has done exactly what it was meant to do. This has been the Sleepy Mechanic, and I hope you have a calm and restful night.